start recording. So now I am recording. Okay, so hello everybody, welcome to the 328 midterm review for this year.
Recording in progress.
Okay, meetings are being recorded. That's good. Got it. Okay. I should not click leave meeting on that screen. So yeah, welcome to the 328 tutorial. We will be doing the 2018 midterm, and so first of all, the recording is like available. I'm recording, and I will post it. I will post it on my YouTube channel, which is just my name. Okay, so it's just my name. And then the PDF will be posted in the description, okay, of that video. If you want, you can also take a look at my website, tutor.ca/notes, and where you can find a lot of notes for previous courses that I've taken. So I'll just show you that quickly. So that's me. But then I have lots of notes for lots of the courses I've taken. I did computer engineering. I did hardware engineering here. So I have a lot of course, like, I typed a lot of notes. So for 328 included, but this was maybe some of my earlier ones, so maybe it's not the most professional, but I mean it's pretty good still. I think I think it's good. So anyways, I have how long? They're pretty long, 64 pages long. So I have a lot of course notes on everything here. So anyway, so I think it's good to. In fact, I'll probably have that up too, just to remind myself of certain things. So that's convenient. So if you wanna have some notes there, that's good. And it was with the Sedekat. That was my prof. So it's the same content. That was back in 2021, I think. Okay, so yeah, so let's look at the midterm that we'll do, and we can just kind of get right into it after. And I'll have the chat open. There we go. Okay, so I have the chat open, and you can ask questions there, or of course you can just unmute and ask me, and I will hear. And so that's also an option. You don't really have to raise your hand because I probably won't be watching for that, but just I mean, you can raise your hand if you want. I guess I have the participants screen open, but you can also just unmute if you'd like. All right, so yeah, so let's take a look at this. So just overview of what's going to happen. We're going to do a little bit of like this like number representation kind of question where there's like addition and subtraction and overflows and things like this. And then octal representation. And then we'll do a little bit of a CMOS question. And then we'll do a question with lookup tables. And then we want to implement this using multiplexers, full adder using a decoder, and then like a multiplexer representation here, right? So we'll maybe do that, and after the break we'll probably take a break. Actually, that's the last question, so we can do that. And question 5. Oh yeah, sorry, there's still question 6, which is just a some optimization K-map kind of situation. So we can do that, but with max terms. And yeah, okay. Anyway, so there's this. Someone says, are decoders on the midterm? I don't know, but it says I haven't seen the exact midterm, but I do. All I'm really focusing on is what was posted as like a list of relevant things, and it says all of chapter 6. So sections on the midterm covered by the midterm are, and then some of chapter 2, some of chapter 3, some of chapter 4, 5, and then it says chapter 6, all sections. And I'm fairly certain that fundamentals of, where is it? Nope, it's not there, is it? Can I just search VHDL? I have the textbook. Just should have had it open. VHDL. Okay, well let me just open it here. Wow, I don't have the textbook. Why do I not have the? Why am I missing the textbook? Anyways, but I know chapter 6 does have it. I don't know why I don't have it on this computer. So strange. Let me open it up, I guess, here. So regardless, that is in chapter 6. I don't want to this. I don't think Reza has gone over chapter 6. Okay, so we can maybe. I'm not sure. This is what was given to me as a set of information. So anyways, we can focus on other things first, and then kind of move on to that. So, yeah, I don't know. Why don't we just get into it and see what we can do, and then if we have questions or anything like that after that, just let me know. Okay, so question 1, it says, I guess I can just take a screenshot of the actual thing. So it says, assume x is negative 73 and y is positive 57. Find the 2's complement representation for each 8-bit binary. So if it's positive, then the 2's complement is just the binary value, right? But if it's negative, then we do the 2's complement of it, right? So really, we need to convert 57, which is in base 10, to binary. And you've probably been doing this for a while, but let's just practice it once. So you do a bunch of dividing by 2's, right? So you have like 57, and then you keep dividing it by 2. So dividing it by 2 is going to be like, what's going to be 35 or something like 36.5. Yeah, that's what it is, 36.5. And it's like, if ever we have like a decimal, if we have a 0.5 essentially, then that represents kind of like a 1 in the expansion. And then we just kind of keep going through like that. So 36, that number pulls down, right? And then what is this? 18. 18 doesn't have a decimal after the ones position, so it's just a 0. Then 18, we keep dividing that by 2, right? Dividing that by 2, we have a 9. Still doesn't have a decimal. 9 divided by 2, it's a 4.5. It does. 4 divided by 2, it's a 2, which does not. And 2 divided by 2 is a 1, which does not. And then I think we go one last one, which is like a 0.5, and then we have a 1 here, right? And then that's pretty much it. So then to read this back, you kind of go like that, right? So we want the number 57, right? So we kind of go like we read kind of like, so 2, 3, 4, right? So this goes here up to this goes here, like that. So it's going, is it, hold on, I got a cat that's, yeah, is someone's, shouldn't it be 28.5? Is that just wrong? Yeah, I mean, that is just wrong, isn't it? Right? Because that's 25 and then 28.5. Yeah. Okay. So then, but this does end up being 57, right? So, or does it? Yeah, it does end up being 57. So something, yeah, that does make sense what you're saying. Oh yeah, sorry. It's 57. Yeah. I'm doing 57. My bad. I'm doing 57. So 57 is 28.5. The decimals ended up being the same. 28.5, right? And then we have that this is 28. My bad, guys. And then this is going to be 14. Okay, now we're getting the brain going, and we're not going to make silly mistakes. So this is 1, 0, 0, right? And this is 7, and this is 3.5. And then this is 1, and then this is 3, and then this is 1.5 is 1. And then this is 1. And we have 0.5, right? And this is 1. Okay. Now we did it, right? That's what it is now. I was doing 73. And then we do a similar kind of thing. So we have this number over here goes there, and this number over there goes there. Hopefully that makes sense. I might have one off now, but anyway, so it's going to be 1, 1, 1, 0, 0, 1. And so you see the pink thing goes there, right? And yeah, so then from here, we, I mean, that's the number in base 2, right? So just to confirm here, right, we should get 57. So this is going to be, 1, 2, 4, 8. 16, and 32, right? And in fact, that does add up to 57. Okay, so that's our kind of way of doing it. And the only thing to really remember is that last bit where it's like you kind of shift it like that. So the bottom is like the yellow bit, and then we have that there. So that's 57. But it says 8-bit binary. So to convert it to 8-bit binary, I mean, right now it's just 7 bits. It's not even 7 bits. It's 6 bits. And so to make it 8 bits, we need to put just like 2 more zeros. So we put it kind of in the most significant bit section. So now it's 8 bits like that. So hopefully that makes sense. Okay, so that's 57. So all we did so far was convert 57 to base 2. So now let's convert negative 73, right? So now we do negative 73, which is in base 10. We want to convert that to binary. And so we just do it to 73 first, right? And so we do the same kind of process. So let's just do that quickly here, right? We do it to 73, right? So 73 divided by 2. This time, it is, in fact, 36.5. Corresponds to a 1. And then we keep dividing that by 2. So we just take the whole number part, right? We just take the mod 2 part. And so we have 18, right? Now the numbers are correct, right? So now we have 9 over 2, which is a 4.5. Oh, sorry, 18 already divided by 2, which is 9, which is a 0. We have 9 divided by 2, which is 4.5. So I'm kind of doing this fast, but hopefully it makes sense what we're doing. This is 2, which is going to be a 0. 2 divided by 2 is 1, which is going to be a 0. And 1 divided by 2 is going to be a 0.5, which is going to be a 1. So then, again, kind of reading bottom to top, left to right, this will end up being, so we have 1, 0, 0, 1, 0, 0, 1. And again, I'll just kind of mark that and that. Okay, so we have this. Now we need to make it 8 bits again. So 8-bit binary this is currently how many bits? Well, it's going to be 7 bits. So then we need to put just one more 0. So we'll do that right there. Right? And now that is 73 in base 2, right? And like the little subscript is just like what base we're in. And so now to do 2's complement, so just you have to remember how to get the negative 73 in 2's complement form. So there's like a few tricks of how you can do it, but the way that I just always do it is I just flip everything and add 1. So invert everything. So it's 1, 0, 1, 1, 0, 1, 1, 0. And then I still have to add 1. So you can kind of think of it like maybe adding 1 here, like that, right? So it's going to be 1, 0, 1, 1. And now I'm going to add 1, so it's going to be 0, 1, 1, 1, like that, right? And yeah, so that's negative 73 now. So that right there is the 2's complement binary representation of negative 73. 73. Why am I saying 72? What am I saying? 73. Well, it says 8-bit binary. So someone's asking, why specifically base 2? Because it says 8-bit binary. Could ask you for hex or something like this, which is true, but yeah. So the conclusion of the question is that 57. So the variables were y was 57 in base 10, in base 2, 8-bit base 2 binary, 0011, 1001. So it's 0011, 1001. And then x, which was negative 73 in base 10, was the one thing we just found right here, right? There we go. So it's 1011, 0111 in base 2. All right, so hopefully that makes sense. Kind of just a bunch of conversions, but the part that's maybe, so converting to binary, I think you've done before in previous courses, but maybe not the 2's complement, maybe even the 2's complement. I don't know, right? But it's just important to just remember how to do that because that's like what the computers are doing, and it's the best way to understand 2's complement. Really is just inverting everything and then adding 1, because that's how we do it in like an adder, right? In lab 3, in the adder, we have that kind of sitting there. So that's how we implement like a subtraction operation, like adding a negative. So yeah, so that's just something to consider. So then part B, so I'm going to keep moving unless somebody stops me. So if there's anything you want me to clarify or anything like that, you can always just unmute and things like this, right? But yeah, okay, so someone's asking, what about 57? Well, we did 57, but it's positive, right? So there's nothing to do to 57. You just converted it to binary, and then that's everything. But in the next part of the question, right, so 57 is just what we have here, 0011, 1001. But, well, the 2's complement of a positive number is just a number. There's nothing to do. So it's already in like a 2's complemented form, right? Yeah. So, okay, so calculate the subtraction. Well, here we have to do something a little bit different, right? So A is going to be x minus y. So x was negative 73 minus, okay, so, but we don't really subtract things, right? We just add the negative of 57. Y was 57. So the actual answer here is going to be like negative 130, but we need that in base 2, and so it subtract the 2's complement of this. Calculate the subtraction in 2's complement. So that doesn't mean just like convert this to binary. That means like use the 2's complement forms of these guys to actually compute the binary of negative 130. Because we'll just keep it in the back of our minds that negative 130 should be the answer, right? So I'll just kind of leave that over here. But that's not actually like, we're not done. So we need to take the 2's complement form of negative 73, which we already have, right? So I guess I'll just write that as this. X is 1011, 0111. And then negative y is going to be something, right? So y is 0011, 1001. So we need negative y though, right? So negative y, again, you flip everything and add 1. So 1, 1, 0, 0, 0, 1, 1, 0. But we need to add 1. So of course it's just 1, 1, 0, 0, 0, 1, 1, 1. And now we can do our actual operation. We can do x plus negative y, right? So we can do x plus negative y. And so that's going to be 1, 0, 1, 1. I'm just writing x, 1, 1, 1. And then negative y is 1, 1, 0, 0, 0, 1, 1, 1. Right? And then we are adding them like this. Okay. So now we can just do this addition over these 2's complement forms. So let's take a look, right? So, and it's important to remember how this like full carry adder, like a full adder is working. So we have like no carry in, right? C in is 0. And so, I mean, in a way you kind of have a carry in, but anyway, so we have it's like this is basically like an adder at each step. And so, okay, so let's just go through it. So, 1 plus 1 is going to be 0 carry 1. So I'll just write it like that. 1 plus 1 plus 1 is going to be 1 carry 1. 1 plus 1 plus 1 is 1 carry 1. 1 plus 0 plus 0 is 1 carry 0. Similarly, and this is going to be 0 carry 1 out the side, right? So this is our last carry bit out on the side there. So yeah, okay. So anyways, that's kind of our value here. And so let's just check what's going on here, right? This hopefully is negative 130, right? Is negative 1. Should be, right? So we're going to take all the bits, including this kind of overflow bit, right? We're going to take this kind of overflow bit here, although it doesn't really matter. So I kind of just like bring the overflow bit down, right? And so this is our, this is our A, like the answer A is 1, 0, 1, 1. Well, I should write it a little differently. 0, 1, 1, 1, 1, 1, 1, 0, right? And then again, I want to convert this. I just want to see if this is negative, if this is negative 130. So the way I can do that, this is the answer, but let's just check if it's negative 130. So the way I can do that is I can just do the same thing. Like to get in and out of 2's complement, it's the same thing. So I'm just going to flip all the bits and then add 1, right? And it's going, so that's going to be 0, 1, 0, 0, 0, 0, 0, 1, 0, right? Because the 1 kind of adds up. And then what is this? This is 2 plus 128, which in fact is 130. Positive 130 because we did the 2's complement, right? So that means this original number before we did the 2's complement is in fact 130. But yeah, so you can see that we have like a, the number's kind of too big because of this overflow that's kind of happening, right? And so the next part of the question is going to be asking about that. But before we do that, I guess, that, like, just to be clear, the answer to the question is that. Like, that is the answer to the question. So hopefully that makes sense. Okay. Again, I will just keep moving unless anybody asks me questions or anything like that. So yeah, let's see the next one. Okay, so it says if an overflow occurred in the above operation, did it have, explain your, like, did it have an overflow? Explain your answer in not more than 3 short sentences. Okay, someone's explaining here. Someone's asking 2 questions I got just now. So let me go back to these questions. So yeah, so someone's asking like 1 plus 1 plus 1, right? So yeah, so if I have 1 plus 1 plus 1, 3, right? So 1. So if I have like a stack of 1 plus 1 plus 1, right, adding that together, right, then that has to be, I mean, that's 3. Like, let's just say it's 3, right? So 3 in binary is 1 1 1, but it's kind of like, it's like 1 1 in one position. So you have to carry this to the next bit, right? So it's 1 carry 1. 1 1 1 is 1 carry 1 because it has to be 3, right? So 3 is 1 1, and then you carry this other bit up because there could be some other operations here happening. So hopefully that makes sense for 1 1 1. And then why is it positive 130? Positive 130 is not the final answer. Like, this is the final answer, which represents negative 130. I was just making sure. I was just making sure that this actually is negative 130. And the way I made sure is I 2's complemented it, and then I saw that I got 130. So that original number must have been negative 130. Can I explain the carry stuff again? Sure, I can explain the carry stuff again, right? So the carry stuff is basically just like when I do these operations. So if I'm just, so let me maybe move this down a little bit. Why can't I convert that number instead of 2's complement? Do you mean this? Which number? Do you mean this number here, or do you mean like convert? Well, but it's in 2's complement form, right? So we know the numbers has to be negative here, right? So we get it out of 2's complement form like that. Yeah. And so then someone's asking about the carry stuff, right? So I can just briefly explain the carry stuff, right? So I mean, I just like, addition of binary numbers, right? So if I have at most I can be adding 3 things at the same time, right? So I can have like an X, a Y, and then like a carry in from the previous one, right? And then I have like a sum and a carry out to the next one, right? Like same with like regular addition, right? Like same with like if I'm adding like 227 plus 35 or something like that, right? I have digits that I'm adding, and they turn into a sum, right? So this is like 12, and then I have like a sum, which is the 2, and then a carry out, which is for the next bit, and that carry out is a smaller order. So I have a sum and a carry out. So I still have a sum and a carry out. So like we just go through all the options, right? So there's like 8 possible options. 1 1 0 1 1 1, right? No, 1, yeah, 1 1 1. that 8? Yeah, that's 8. Let me move this down here a little bit. So we have 1, 1, 0, 1, 1, 1. And so if I'm adding a whole bunch of 0, then of course everything out will be 0. If I'm adding just a 1, then anywhere there's only 1, 1, the sum will be a 1. That's it. And the carry out will be a 0. Right? There's only 1, 1. So just the sum will be 1, and I'm not carrying anything out. But if there's 2, then 1 plus 1 is 2. So my answer is 1, 0. So that means my sum is 0 and my carry out is 1. So if there's 2, it's going to be 0, 1, 0, 1, 0, 1. And then just the weird thing that happens is when I'm adding 3, I already described it up there. So my answer is 3, so it's 1, 1. So my sum is 1 and my carry out is also 1. So that's just like a full ladder. And we're basically just implementing that by doing it by hand. Okay. For the extra zeros, you just put those on the left side because the 8th bit, because you only had to say, just making sure. Yeah, like you have to put on the left side, right? Because it's like the number 375 is the same as the number 375, right? It doesn't make a difference. So the most right digit is your sum, and the carryout is the one next to it. Yes. There's only ever going to be 2 digits, two bits, right? So, yes, correct. Yeah, good. Okay, and then yeah, someone's asking about 2's complement. So let's maybe finish this question, and then I'll get back to you because I think 2's complement comes up a little bit later again. So we can talk about it there. But let me just finish this part of the question just with the overflows and stuff like this, and then we can maybe come back. So if an overflow occurred in the above operation, explain your answer, right? So does anybody know how we can tell? How do we know if the overflow occurred in this operation? There's just like a way that we can compute it. But I don't even need the formula because actually the next question is give the circuit to detect the overflow. So these questions should really be one question, right? But they're really the same thing. So it really is just a thing that should be known, and it's kind of derived in the textbook and things like this. But it's basically just that these 2 bits don't match, right? So it's about those 2 bits matching, and so the bits matching means that they have no overflow, and if they don't match, then there was overflow. So so we can just kind of say that, right? So it's like if the last 2 carry bits don't match, and so there was overflow. And so we see that the last bit here is kind of like a weird example because not weird, but like it's just like there's more illustrative examples. But the last bit was a 0 here, right? And so, but in general, like we needed 9 bits here, right, to compute it, even though the last bit's a 0. So technically we didn't, but you don't know that going into like in general, right? So that's kind of the idea of why we needed another bit there. And yeah, and so we need that bit in the front to indicate to us that it's negative, right? So hopefully that makes sense. And yeah, so okay, so that's that. And so then give the circuit to detect the overflow. Well, how do we check if 2 bits match? What circuit tells us if I have a bit A and B, and I just want to know if they match? Or I guess I want to know if they don't match, really, here. And wouldn't quite work because someone suggested but and wouldn't work because if I had 0, 0, I'm saying I want to know when they match. So that should be a 1, but that's not true. That's not true for and, right? I guess I really mean when they don't match, right? So when I have two signals, A and B, right? Yeah. So someone said someone said XOR, so I agree with you, right? So if you have XOR here, then this is exactly what we're saying, right? So if they don't match, then it's going to be a 1. But if they do match 0, 0, or 1, 1, it's going to be a 0. So that's kind of the circuit. So we just need to check like the last carry and the second last carry. And that's going to be kind of our overflow, right? Overflow bit. And yes, there was here. They don't match. So hopefully that makes sense.
So can we go up a second?
Yeah. To here or what? To where?
There's one more. I just wanted to see where they didn't match.
Yeah, here. Let me turn on my fan. It's kind of hot in here. Let me turn on my fan. Wait. So yeah, so that's that. Okay, so then there's one more part to the question. So it says convert result of B to octal representation. The result of B was this guy, right? So this was the result of B. And so we can convert it to octal. So let's talk a little bit about this. And so I'll maybe also show you like how to convert to hexadecimal at the same time, right? So we have like binary, right? Binary is base 2. We don't really talk about base 4. We have octal, which is base 8, and we have hexadecimal, which is base 16. So we'll talk about these last two, octal and hexadecimal. Hexadecimal is really the most important one, so we do almost everything in hex later on. It's just much more convenient. Binary is just really long strings, right? So if you have 32 bits, then the only way to describe that precisely is with 32 symbols, right? Well, that's not true. If you use octal or hex, notably hex is probably the best one. And hex is kind of the best middle ground. So the thing with octal is you use the numbers like 0 to 7, right? And hex you use the numbers 0 to 15, but we don't actually use like 10, 11, 12, 13, 14, 15. We use A, B, C, D, E, F. So we add like extra symbols there. So we'll just do both. So let's just do octal here. So for octal, you take the number octal 8. 8 is 2 to the 3, right? So you make groups of 3. I guess really, sorry, it should be clear. You go the other way, right? So you go this way. You make groups of 3, and then you just convert that to binary. So right, so like we just do each one individually here, right? So this is going to be what 2 plus 4 is going to be 6. So this is 6. This is going to be 7. Just one more. And there's going to be 1 plus 4 is 5. So that number is 576 in octal. You can kind of just group it like that. And the highest digit you'll have is a 7. So hopefully it makes sense. The groups of 3 that I grouped together. And then in hexadecimal, which again is really the important one and the one that you use almost always. Like it's really binary at the end of the day. Like the circuits are all binary circuits, but just to write it, we use hex. Hex is 16, so it's base. It's like 2 to the 4, so we make groups of 4 this time, right? And then we're missing 1, right? So I just toss on a couple zeros here, and there we go. And now we convert this to hex, right? And so, yeah, correct. The 2's column doesn't affect it, so it's just like the like the representation of the number back into this form like this, right? That's not equal to 576 in base 10. It's just a representation. It's just another way to write the number. That number might still be negative, but it's just another way to write it. So then we convert each bit here, right? So just remember that it's like, you know, 1 is 1, 2 is 2, all the way to 9 is 9, but that 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So then we convert that, right? So this is going to be what? 2 plus 4, 6, plus 8 is 14. 14 is E, so that's going to be an E there. 1 plus 2 plus 4, right? It's going to be 7, so 7. And then this is just 1. So that means that it's this number is equal to 17E in base 16, but we don't ever write it like that. So we just say we write 0x17E. That's just that means this is in hex. Anyways, maybe you don't have to remember that, but this is just converting to hexadecimal. If they ask you to convert to hexadecimal, they might. That's like just a variant that they could do. How are you counting it? What do you mean exactly by counting it? Like, how am I determining this is 7? I just like convert, like I just convert these numbers here, right? So this is 1 plus 2 plus 4, like as if 0, 1, 1, 1 was just a binary number. So then that's going to be 7, right? Here it's going to be 2 plus 4 plus 8, which is 14, and 14 is E in hexadecimal. Same thing like up here. I just did it in groups of 3. So anyways, we have other ways kind of writing it, so that's good. So just, in case they ask you for hex, then you have it in hex. Yeah, So I don't mean to confuse, like, ignore this if this is confusing, but it's just like, that just means hexadecimal. That means the next thing I'm going to write is in hexadecimal, 170. Right? That's just like the symbol we use. I don't actually really know the origin of that, but that's kind of just so if you're talking about like addresses in memory, it's like 0x, just like the hex address. Okay, so well, that's that. So let's keep moving. Again, I'll just kind of keep going unless somebody stops me. So the next one is like a CMOS question. Oops. Here we go. Oh, that's not what I meant to do. Where did I click? There. Yes, correct. Zahim, correct. So this is the next one. It says implement the following function f, which is here, with a minimum number of transistors. So whenever it says minimum, like for the most part, you don't have to stress too much. If you know how to do it, you probably know how to do it with the minimum number of transistors. There's only a couple details where you have to think about where you might not be doing it ideally. Just to kind of like give you an analogy, it's like you're finding the domain of a function. It's like it's probably all real numbers, but there's a couple situations you just have to look out for where it's not. So like if you're dividing by 0, or if you're doing a square root of a negative number, or log of a negative number, or something like that, right? So it's there's certain things you have to look out for. So I'll just show you. There's only one thing to really look out for in this question where you might not be doing it ideally. Okay, so let's look at it like this. Okay, so first of all, our function, right? What's our function? Like just the common name of our function, f. Oh, someone said, are we covering decoders? That was my plan, but some people are saying that Reza didn't get to chapter 6. I'm not sure. Yeah, so I don't know. We'll see when we get there. So the function is just x1, x2, as people are saying, right? And so the negation of our function is going to be not x1 or not x2. Maybe we can do that quickly just in case people are confused. So it's the negation of that. And so then De Morgan says it's this. Mr. De Morgan's, as it says. And so when we implement with CMOS, so CMOS is like combinational MOSFETs. So the point is that we're designing like a circuit using actual MOSFETs, and we have like MOSFETs aligned in either in series or parallel in some kind of complex orientation, or we have that. And also we have like PMOS and NMOS as two different components. How did we get F again? Kind of just by looking at the lookup table here, right? So the lookup table works like, the first number is for when the inputs are 0, 0, 0, 1, 1, 0, 1, 1. Yeah, so someone else asking the same question. So it's like the lookup table is just short form for this table. X1, X2, right? Or you could do it the other way around too. I guess it's X2, X1. And so there's all the zeros here. And so we only get a 1 when they're both 1, so clearly it's an AND. Like this is what the function for AND looks like, right? Like it's zeros for everything except if they're both 1. Okay, so then in general, right, we have our signals X1, X2 coming in. And then we have like VDD along the top. And then we have ground along the bottom, right? And we implement our F inverse. There's a few ways to do it, but this is like the minimum number of transistors kind of way of doing it. So we implement our F inverse here and implement our F here. So both of these kind of go to both of these, right? They kind of like, both of them need it. And so then here, what we're going to get is F, right? F inverse, sorry. We're going to get F inverse. And then we need to put it through like an inverter, basically. And then we get F. So this is like this is not the drawing. This is just like I'm just giving a plan here, right? This is just like our plan of action here, right? So, and we'll see why this is more efficient. You could flip these, right? And then you wouldn't have to have this inverter, but actually it's better to have the inverter. Okay, so yeah, I will explain. Well, okay, just looking at the picture, the inverter at the end, right? I mean, we have F inverse here coming out, but we want F to be coming out, right? So I need to invert it to get the other way. But like, why do we have F inverse here? We'll see that in a second, right? We'll see that. So let's start drawing it. So our X1, X2. Okay, so I need to draw. I have VDD up here, right? This is like our positive 1. So I'll do our inverse here. So it's not X1 or X2, right? So we have the signals not X1, not X2. And we want to OR them. So OR is always like in parallel. And remember, with the pull-up network up here, we always are using these PMOS MOSFETs. And they have like an inverter built into them. This is kind of the point of what we're doing like kind of optimally here, right? So this will be connected to X1 and this will be connected to X2, but naturally it's already going to be inverting them. Like I don't have to invert them to make it not X1, not X2. It's going to be inverted right there. So then it's ORing them already. So we don't have to invert those signals individually. We don't have to like have a separate inverter to find not X1, not X2. We're just going to use the inverters that are built into the PMOS, right? So that's the top half. The bottom half is just the AND of the two, right? So we're just going to have here NMOS, which does not have an inverter on it. And so you can just kind of like put a little line and say what it's connected to, because otherwise the picture gets really messy. You could also have X1, X2 over here and then connecting them up. And so this is it essentially, right? And so here we have F inverse coming through. So let's just like make sure we understand what's happening there, right? F inverse is coming through. So if the signals are 1, 1, right? Like X1 is 1, X2 is 1. Then what's happening here, right, is we're going to get, it's inverting right there, right? It's inverting right there. So it's going to be 0, 0. So neither of these paths are going to be going through. So this is not going to be connected. Whereas here, you can see where my mouse is, I think, right? You can see where I'm circling. So anyways, there and there, right? These two, they'll both be 1. So this will be connected and we'll get a 0. 0 meaning ground, right? VDD is 1, ground is 0. So we'll get a 0 here. But that's exactly the opposite of what we want, right? And so the same thing will happen if we have any other combination, right? So let's say we have 0, 0. So if this is 0, 0, then clearly these are both not going through. There's no power going through either of these ones, right? This is kind of like just controls if. So maybe I should mention that actually, right? So the point of a NMOS, right, is like if I have a 1 here, that means that like electricity can flow through, and if I have a 0 here, then electricity cannot flow through. PMOS is the opposite. So PMOS has like a little inverter on the top, just to kind of remind you. So if the input is a 1, then electricity cannot flow through, and if input is a 0, the electricity can flow through. So that's for PMOS, and this is for NMOS. And so that's what's happening here, right? So the point is like if I have 0, 0 as my inputs, then neither of these can pass through, right? But here, both of them can pass through, right? It's 0, so electricity can pass through both of these. So that means that this will be like a complete, like a short circuit for here to here. And that means that F inverse will, like this node right here will have voltage 1, like a logical value 1. So this is almost done but we want F, not F inverse. Oops, we want F, not F inverse. So to do that, for example, if x1 and x2 were 0, F would be 1. Yes, correct. Right? Correct. So exactly the opposite of this table. It would be 1, 1, 1, 0. So we make a NAND gate, then a NOT gate. Well, we don't have a NAND necessarily. Why do we have a NAND gate? Oh, I guess because it's inverting like that. Yeah, so we just want to invert it again, right? So we made a NAND gate here, and then we want to invert it again. Yes, that is correct, everyone. Yes, that is what you're saying is correct. So we have a NAND gate here, and then we need to invert it one more time. And that's more efficient. So the thing is this, right? So remember that we could also have done something a little bit different, right? Instead, I could have put the pull-up network here. I could have put like the AND here, right? These two, these two here with PMOS. But I would have had to invert them first, right? Because I need not X1 and not X2, because there's an inverter built into the PMOS here, and it has to be PMOS on the top, just because of the structure of it. So I would need more inverters, whereas here I just invert it at the end, and then that works, right? So inverting it at the end would look like this, right? So I have another VDD, I have a PMOS, and I have a ground, and then I can just connect it like this, right? So maybe I should draw like a little bit more accurately, right? And then this is going to be our F, right? Because if F inverse is 0, that means that there is power going through this way, right? Which means that this is going to connect, and this is going to be becoming a 1, whereas opposite is going to become a 0. So this is like, just to kind of color code what's happening here compared to this diagram, which was kind of like the plan. So like that, kind of a harsh color. Maybe I'll just kind of box it like this. That's kind of that. That's kind of that. And then, that's kind of that. Hopefully that makes sense. Okay, so questions. NAND gate. So how do we know that F naught is the output? Well, that's kind of what I was going through, with trying some examples here, right? But it's also just like how I set it up, right? So I put whatever you put on the top will be the function. So you see how I put the inverse on the top, right? I put not x1 and not x2 or not x2 on the top. So whatever you have on the top will be the function, because that's where 1 is, right? The point of the pull-up network, this top is the pull-up network. It's pulling it up to 1. But if I put the inverse function there, then the inverse is going to be pulled up to 1. And then I just invert it. But this is much more efficient than if we just put the regular function there, because we need less inverters. So the PMOS circuitry can only be at the top of the circuit, correct? Yeah, what if the terms in the equation were already complemented? Yeah, there might be some other situation where you know, it might not be so clear. But like in general, if you have like one of the expressions with a bunch of inversions and like the individual values being inverted, and then you have one with not, then like not with that, like not inverted, kind of a silly way of saying it, but you know, they are not inverted, then you do it like this. You put the inverted ones on the top and the non-inverted ones on the bottom. The expression with the inverted ones on the top and the expression with the not inverted ones on the bottom. In what case would we not need an inverter? Well, if you put F here, right? So if you put, not F inverse, but if you put F there, then you don't need an inverter. But then you will need to invert X1 and X2 on the way in, right? So we can take a look at that. We can see maybe it makes more sense if we look at that too. They give the pull-up network the inverted version, but if it's given to you without being inverted, then that's the pull-down network, and you have to invert to get the pull-up network and also invert the F because you want the normal output. That makes sense what you're saying? Is there a question? I don't know if there's a question there. I think that correct. They give the pull, if it's given to you without being inverted. Yeah, that makes sense. Yes, that makes sense what you're saying. Yes, good. Instead of writing VDD, I just saw some places use a flat bar. Is that the same? Yeah, it just means the same thing. It's just like, you know, there's like some actual piece of metal in the circuit that you can connect to, and they're just drawing the piece of metal, I guess. Not for necessarily every CMOS circuit, but in general, we like to do things with like a couple, like one extra final inverter if it makes the earlier things easier. So I can't say for every CMOS circuit, but often. So the output function is always the PMOS one. Yeah, right, because that's the one that's being pulled up. So you see here, it's like not the thing coming in, right? Not the thing coming in. So not F is F. And so it's a thing coming in. But respecting the fact that there are inverters here with the PMOS, right? That's important. Correct. The pull up network is PMOS and the pull down network is NMOS. Correct. That is correct. Okay. So that's that. Let's see, more questions. Why does PMOS have to be connected to VDD and NMOS to be connected to ground? That's just part of the structure of like how we write CMOS circuits. That's becoming a little bit of a more electrical question, which I appreciate, but I don't particularly know the answer to. It's some electrical reasons why we do it in this particular order. How exactly does moved? How exactly does pull up and pull down work? Like, is it just PMOS and NMOS? Yeah, I mean, it's just what you're saying, right? So like we call the pull up network. So remember, like the network is just like a series of gates of NMOS and PMOS, which are our gates. And if there is a connection between the center point and VDD, the logical output's 1. If there's a connection between this center point and ground, the logical value is 0. Here, like the logical value at this location is 0. So the pull up network is pulling it up to 1 if that's the case, pulling like the voltage up to 1, logical 1, and pulling this down to 0 if the logical value should be 0, and then that depends on it. Now we of course don't want both of them to be connected at the same time, right? That would be very bad. So they should be mutually exclusive, as they are here. So can you please explain why the inverter works if we say F0 is 1? Sure. Right? So if F0 is 1, if we have a logical 1 coming in here, right? So logical 1, let's follow it down here. Logical 1, right? Then we have electricity can pass through this NMOS, right? And so this logical value of 0 is being sent here. Let's follow it up here as well. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Here now it gets inverted to a 0, right? And so it cannot pass through, right? And so there's no connection here. So there's only a connection between F and 0, which means our logical output is 0. Like F and ground, which means our logical output is 0. Yes. So the PMOS inputs will always determine if we invert again. That makes sense to me. Reza said our exam was MCQ, but we should have to show our work. Would it be safe to assume he won't ask questions for converting to different types of circuits, less drawing circuits, since a circuit cannot be an option for multiple choice? Oh, that's tough, right? So he said it was multiple choice. Interesting. I had also multiple choice when I took this course. And there were some circuit questions. And so yeah, you're supposed to draw it. Does he ask you to submit it? He asked you to show your work and submit it. I'm assuming. I don't know. I'm not claiming that. I don't know. He didn't tell me. But yeah, so he does multiple choice midterm. That's interesting. That's kind of a new thing since COVID, I think, that he's been doing. So but don't underestimate a multiple choice. That doesn't mean that that there's not going to be circuit drawing and things like this. You might have to draw a circuit. You might have to draw a circuit to understand. You might have to draw it just to understand what's going on in the circuit and things like this. So yeah. Okay, so that's that question. So yeah, he says show your work for marks. Okay. Yeah, not every case needs an inverter. Someone asks if every case needs an inverter. It's just if this is F inverse that you're implementing up here, which we did in this case because we have a lot of knots in F inverse, which makes sense to be put in the PMOS section. And so this is the detail about minimum number of gates of transistors. Like if we did it the other way, if we put F up here and F inverse here, then we wouldn't have the time to we would have to have another 2 inverters to invert X1 and X2 up here, because it should be it's supposed to be like, let's just imagine it was flipped. It's supposed to be not and not here, right? If this was on the top. To get that, I need an inverter for each one. So I need 4 additional inverters, 4 additional gates, I guess. So yeah, 2 additional inverters, 4 additional gates. So yeah, that's kind of detail there. Okay, so it's 11:11. So why don't we take a little break and then we can continue with this. So I guess I will skip the decoder question maybe, but we'll see how it goes. I mean, we can still maybe do it. I don't know. Just as a detail. If only maybe it's only on the Vadim test. I don't know. And so maybe the tests aren't the same because oh no. The exam format is problem solving with final answers given in multiple choice format. You must provide exams without provide 0. Yeah. So never mind. Both tests are the same. So I think, So I think, I think it's the same between both profs. It seems like the same instructions and chapter 6. So we will do the decoder then, just as a detail. Okay, guys. So let's take 5 minutes. Okay.
Recording stopped.
Someone's now saying Reza did cover decoder, so we will do the decoder question. Okay, so we'll take 5 minutes maybe. So 1:17 we'll be back, and then we can continue on this. So let's get back to it.
Recording in progress.
We're here and recording's in progress. That's good. So let's keep going. So we did our make the chat open again. And I'll have this open too. Okay, good. So let's keep moving. So we did this CMOS question. Let's do our third question. So it says implement a half adder using only 2 input lookup tables. So remember how a lookup table works, right? So a lookup table in general, right? We have a series of kind of like so it's a 2 input lookup table is going to be like A and B, and we have an F coming out, and then here we have our different values for A, B, right? So if the value, maybe we can write it like this, right? So the table kind of looks like this: A, B, 0 0 0 1 1 1 0 1 1, and then you can decide what goes here, and that's your function, right? So this could be like 0 1 1 0 F, and then this, which we usually just write a triple equal sign to be kind of the same. We usually kind of just write it as 0 1 1 0 with an A and a B coming in and an F, right? We don't draw the whole table, like it's just implied that the 0 0 0 1 1 0 1 1 is the order that it's written in for A and B, and then and this is of course an XOR, right? A function here like that. So this is just an example of a lookup table, and it's just kind of a convenient way to write down a function. You know, you would do some kind of K-map or something like that to actually implement the function here, but you can do it kind of however you want to do it. When asked to make a CMOS from a function, do we need to invert it like in this question? Yeah, like probably yes. Now you just pay attention to whichever function out of f or f inverse has the most like inverted variables. Then that's the one that you want to put on the top because that's where the PMOS is, right? So this one's a very clear choice. There's only this one has all the inverted variables and this has none. So very clearly that one had to go on top. So hopefully that makes sense. So then implement half adder using only 2 input lookup tables. We have to remember what a half adder does, right? So a half adder, you know, is a module, right? The module has a x and y bit, so it's adding 2 bits, but it has a sum and it has a carry out. It has a sum and a carry out. It doesn't have a carry in, right? The full adder has carry in. So the point is that when we draw the table, so I use like a little double line to separate inputs and outputs. So we have x and y coming in. Then we have like a sum and a carry out. So if we have, 0, 0, 0, 1, 1, 0, 1, 1. So S would be XOR and CL would be AND. I mean, that's correct, right? So but we can just kind of fill it in like usual. So 0 plus 0 is 0, carry 0. 0 plus 1 is 1, carry 0. 1 plus 0 is 1, carry 0. 1 plus 1 is 1, carry 1. Right? Is 0, carry 1, sorry. And so you just kind of fill it in like that, like you're adding. And so, because it's a half adder, so it is adding. That's the point, at least. And so now, right, the point is that we want to implement this using only 2 input lookup tables. That's fine. So we're going to have like input x and y, like this. And then there's going to be 2 input lookup tables. And so 2 input lookup tables basically are a list of 4 numbers, right? So they're going to be 1 for each output, right? So we're going to have a 1 for 0, 1, 1, 0. And we're going to have another one for cout, 0, 0, 0, 1. The output of this will be S. The output of this will be cout. X goes here, Y goes here, X goes here, Y goes here. And we're done. That is a half adder with 2 input lookup tables, but it didn't actually say 2, so it just says only. And like, yeah, like S is an XOR and cout is an AND, but we can only use lookup tables. Well, that's what it is, right? So like lookup tables are just kind of a convenient way to implement a function. Again, internally they're doing something, right? There's some K-map that's happening internally to those rectangles, but that would be my answer for this. Okay, so hopefully that's okay. What's going on there? Okay, a bunch of questions. That's good. So can you explain how you made the table? I just made the table based off of the numbers that we saw here. Oh, unless you mean how I made that table, the table up there. So like, how did I make these tables? That's how I made these tables. The color coding. How did I make this table? Well, that's just what the table for a half adder looks like. But it's like also just like logically we're just adding the bits, right? So 0 plus 0, the sum is 0, the carry is 0. 0 plus 1 is, the sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. 1 plus 1, the sum is 0, the carry is 1, right? 1 plus 1 is 2, 1, 0. How did we know we needed 2 tables? Well, we couldn't do it with just one, because just one, we would only implement one of these 2 functions here like this, right? So, because we have two outputs, right? So, could you explain how you know what the function was? What logic function did you use? So I'm assuming when you're asking that question, you're asking from up here. I think it's the confusion is about the table itself. For x1 equal y1, so I think maybe this next. No, you don't mean there. You mean down here. Okay, and I'm getting a question about question 2, and I will talk about that in a second. But let's just finish this first. I want to know about the top right. So like this one. Yes, I'm assuming top right is what you're saying. So that's the top right of this diagram. I don't know if you mean, unless you mean the top right of this table, but I think
asking about the blue things, the one there in the blue.
Oh yeah, this. So just to be clear, this is not. That might be confusing. That was just me showing an example of what a lookup table. That's just me that's what a lookup table is. In case people don't know what the word lookup table means, right? It's kind of just like this. This is just an example. So I guess I meant that in the color coding of it, but I guess maybe I didn't say it out loud actually. So the color coding. So that's just a side example, just so you understand that what a lookup table looks like that. But that's not part of the question. I mean, it's part of the question. Like you have to know what a lookup table is, but just so you know what I mean when I write a box like this, I mean like a little function that's implementing a table that looks like this. So I think that's what you mean. Yes, thank you to the person who unmuted. Yeah, good. Okay, then for x1 equals 1, y1 equals 1, y was c out 1. Yeah, so it's just like it's kind of just like a binary addition, right? So 1 plus 1 is 2. 2 in binary is 1, 0. So the rightmost digit is your sum, the leftmost digit is your c out. That's always what it is. Like it's always the sum and the carry out. At most your answer is 3, right? You had carry in as well of 1. So that would be 1, 1. We never do 4, right? So yeah. Okay, and then now Mark is asking me about, can you go back to question 2? I uploaded a picture of the answer key on the midterm, but it looks different than CMOS you made. What do you mean? This question? Yeah, but he only got 6 out of 10 for this question. Right? The guy only got 6 out of 10 for the question. He didn't finish the... So maybe that's what you're talking about, Mark? I think, because it looks different, yes, but it's because he got 6 out of 10 on the question. Yeah. Yeah, so I'm like, there's the midterm that I'm following has like a little, like has some errors. So I'm obviously not, not showing the errors. I'm showing my solution that I believe to be correct. Okay, you could have used any other function like an AND gate. Where? No, here I had to use these specific. It had to be these specific ones. Are you? If you're still talking about this, then yeah, this was this totally random. This could have been any random, collection of. This is just an example over here. Example of lookup table not related to the previous to this question, just because we need to know what lookup table is. Okay, so if that's clear to everybody, right, then that's the answer. There's our sum, there's a carry out with 2 lookup tables. How did you know you had to use the specific X, Y, S, C out table? Because it says half adder, and that's what a half adder is. So that's a little bit of just memorization. Like that's what a half adder is. A half adder does exactly this. If I can find it here, I can show you. Yeah, so that's pretty much it. Okay, so that's that question. Let's move on. So the next one is this. So it says implement.
Chef?
Yes.
What was the point in like that particular question like at the bottom? Like, wasn't it just like normal? Like a normal thing? Like, what's the point of it?
Yeah, what like this answer seems too simple, you're saying? Or
yeah, because like we already know like the half adder table, so
yeah, I guess it's just so making sure you know what a lookup table is as well, that you can draw a circuit like this. That's what a lookup table. does. So that's it. And yeah, once you know the half adder circuit, then you know this as well, as long as you know how to use a lookup table. Someone's asking a question. I had a quick question about the CMOS circuit. For example, if I had a function without any NOT gates, I would put it in NMOS and then would have to invert at the end for the original function. What if my gates have NOTs? Can I just make it PMOS and not invert? Yes, you can. But it's just whatever has the least amount, because there probably is some mix of inverting, right? Here there was no mix of inverting, right? Like if I put the NOTs on the top, then I very much have, like, it's perfectly set up for that, right? Because those are just the things being inverted, and then I just invert it once. But if it was like some kind of weird mix, then yeah, you'd have to just make a choice based on like the minimum number of inverters. You want to minimize the number of inverters because that will minimize the number of transistors. It's the only thing you really have control over. So yeah, hopefully that makes sense. So yeah, okay. So then here's question 3b. So implement a 3-input XNOR function using only. I don't know why the word only. I guess only. I don't know why. It's a weird emphasis. Minimum number of 4-to-1 multiplexers. Okay, so let's remember what a 4-to-1. Let's remember what all these things are. So XNOR, right? So XNOR, 3-input, X1, X2, X3. And here I wrote my thing here, right? So, and then it's inverted at the end, right? So that's kind of our XNOR. So this is going to be, you take the XOR of all these, and then you invert it. That's what the XNOR is. So we want to implement this using only 4-to-1 multiplexers. So let's just take a second to understand how would that be helpful? Like, what is a 4-to-1 multiplexer and why would that help us here, right? So a 4-to-1 multiplexer looks like this. So a multiplexer has input bits. So there's 4 inputs here, 1 output, 4-to-1 multiplexer. And since it has 4 input bits, the way a multiplexer works is that we control which particular input is connected to the output. We can decide which one it is, right? Using these control signals. So this is like 0, 0, 0, 1, 1, 0, 1, 1. So if, and this is like A and B, let's say our control signals, right? So if, and this is, X1, X2, X3, X4. So, but maybe I'll just write a 0, 1, 1, 0 or something like that, right? I'll just put something there. I'm kind of putting random numbers. Again, I'm just kind of talking for a second here, explaining what a multiplexer is, and then we'll answer the actual question. So if this is, let's say 0, 1, right? Then does somebody want to tell me what the output's going to be here? Like in this situation, what's the output going to be? A 1, right? So we have 0, 1 is the thing being selected, which means this is connecting. And so we have a 1 coming out there like that. Right? If I made this 1, 1, then it's this one that's connecting. And so we have a 0 here now. So the multiplexer just tells you can have, and these can also be changing. Like these don't have to be hard-coded, but in general, they could be signals. And you can control which signal is connected to the output based on these control signals. So we have these 2 control signals. So of course, if you have 4 input bits, then you need 2 control signals because there's those 4 options, right? So you need 2 bits. Okay, so why is that helpful? Well, it basically lets us implement a function, right? So again, right, basically lets us implement a lookup table. So if I have a function, right, like let me just draw a lookup table quickly, right? So if my lookup table looks like this, then I can exactly draw this as this. And that's identical. Right? Because A and B are kind of just selecting which output we want, and we've hard-coded these, like we've hardwired them, I guess we should say, not really hard-coded, right? And so a lookup table is exactly implemented by a multiplexer of this size, of the right size, and so this is exactly the same thing. So hopefully that makes sense. And so let's just think about it, first of all, in terms of lookup tables, and then once we have it in terms of lookup tables, we can do it in terms of multiplexers after. So the way we'll do this particular one, is we can just kind of think of it in steps here. And it says a minimum, it also says a minimum number. So what we're going to do is we're just going to do it with 4-to-1 multiplexers. And then we're going to ask ourselves if there's some way to reduce the number. That's like my method of doing this, right? It's like, sometimes it's like, don't get overwhelmed by the fact that it says minimum number. Just draw it. Draw what if it works, like something. I mean, you'll get part marks if it's not minimum. But then if you can do it smaller, then ask yourself that after the fact. How could I possibly make this smaller with a smaller number of multiplexers? So what we're going to do here is we're going to kind of break it up into 2 stages. So first we're going to do x1 XOR x2, and then the result of that we're going to basically XNOR with x3, like that. So we're going to do an XOR and then an XNOR, like a 2-input XOR and a 2-input XNOR. So okay, so hopefully that makes sense to people. I'm just this is just kind of an example of using a multiplexer. So maybe why don't I move this down a bit, and I'll just kind of put this kind of here. That's just an example of using a multiplexer to make a lookup table. So we want to implement this function like this, right? So into it we have x1, x2, and x3 coming in. We're going to start by XORing x1 and x2. And the way we'll do that, we'll do it with a multiplexer. So maybe I'll kind of like this. And our multiplexer is going to be 4-to-1, right? That's what we were allowed to use, right? And we want to XOR it. So what would my inputs be here? Somebody want to tell me what do I put here? I want to XOR these 2 values. So I don't have to use Shannon's theorem here. Shannon's theorem is helpful when we have 2-to-1 multiplexers. And probably when we have bigger multiplexers too, but mainly that. 0, 1, 1, 0, right? Because that's the XOR, right? And so now coming out of here, we have x1, XOR, x2. Like that's the value coming out of here. And then to that value, I want to XNOR it with x3. Right? And there's like some symmetry here, so the order doesn't particularly matter. And 1, 2, 3, 4. And so I agree that 1, 0, 0, 1 should be the output. That's the XNOR, right? So XOR is 0, 1, 1, 0. XNOR is 1, 0, 0, 1. And that's it. That's F. Someone's saying we never learned 4-to-1 multiplexers. Okay, I'm not sure. So I'm getting conflicting information here. Some people are saying that Reza covered it. I'm pretty sure Vadim covered it. I don't know. Yeah, exactly. I'm not exactly sure, but we'll just kind of go with it for now. Yeah, how did we get the 1, 0, 0, 1? Yeah, so it's like at this stage, right? What is this multiplexer doing? It is taking the value of x1 XOR x3, like that's x2, I mean, like that's a value that's coming through this wire here. And then through this wire, we have x3. And then what do we want to do? We want to XNOR it, right? I'll do that in blue, right? We want to XNOR it. Then that's what's going to come here, right? And so this is going to be, the XNOR function is 1, 0, 0, 1. Like just remember, like XNOR is the inverse of XOR, right? XOR is this, so the inverse of this is this. He covered 2-to-1. We learned how to use Shannon. That's all. Oh, I see. Okay. Yeah. So I mean, it's similar. So we'll use Shannon's theorem, I think, for the next one, or maybe. Yeah, not necessarily for the next one. I don't know. We could do it for in question 5. It's in question 5. So, but anyways, that's it for 3B. And so yeah, we just have to consider. It says x. It says minimum number, so that we have to ask ourselves if it's possible for us to do it in lower than that number, right? And the answer is no, right? So like 2 is the best you can do because you have 3 input variables. So if you have 3 input variables, I have a cat here. So wants to say hi. I have 3 input variables, and so if there's 3 input variables, then a 4-to-1 multiplexer only can have 2 control signals. So then we're just going to be ignoring one of the input signals if we only have one, no matter what we do. So there's that. Okay. So yeah, I don't know. Yes. Does that make sense? Why? Hopefully that makes sense. Why we only have 2 multiplexers. 1 would not be sufficient at all. So that's kind of my logic as to why it's minimum. There's the cat. She kind of just wants to sleep. She's a little tired. She also doesn't want to look at the camera. I don't know why. Oh. Okay, I don't know. She's a little. She wants to sit with me, but then she doesn't want to be on camera. So she's just gonna sit on my lap. Unfortunately, out of sight. Maybe I can trick her into saying hello. There we go. I can trick her into saying hello. There we go. Okay, so yeah, that's 3B. Is there any questions about 3B? Okay, so that's kind of how we do with multiplexers. Very similar to how we do it with lookup tables, right? We just kind of do it like that. Can I re-explain the 4-to-1 multiplexer? Sure, right? So what time is it, by the way? Still have 20 minutes? Let's go. So let's see. So a 4-to-1 multiplexer in general, right, is, again, a multiplexer is just kind of controlling which input signals go to the output, right? So we have 4 options, 1, 2, 3, 4, right? 4 options, but we'll write that in binary, or I guess 0, 1, 2, 3, I guess are our options. So we'll write that in binary, 0, 0, 0, 1, 1, 0, 1, 1. And, we want to control which particular input is connected to the output at any moment, and it's only one, right? And we want to be able to control this on the fly. So we have these 2 control signals, because there's 4 inputs, so we need 2 control signals. We can say maybe C1, C2. And so if it's like 0, 0, then this is the one that's kind of going in. If it's 0, 1, then this is the signal that's being connected, like that. If it's 1, 1, then this is the signal that's being connected. So you kind of have 4 inputs and 2 control signals that control which input is going to the output.
Wait, sir?
Yeah.
Can you walk me through the one above the multiplexer one more time?
Yeah, this guy.
Yeah.
Yeah, because the trick we're using here basically is that a multiplexer is used to implement a lookup table, right? We can use a multiplexer to make a lookup table. So that's all we're doing here, right? So we have a lookup table. The lookup table is for XOR between X1 and X2. It's the XOR between these two. So we use those as our control bits, and then 0, 1, 1, 0 is that, and then yeah, you're gonna say something?
I said that's the sum values, right?
It's the XOR values.
Yeah, XOR sum value.
Yeah, exactly, right? And then the next one is this XNOR. So similar thing. We need to XNOR the value of X3 with the thing that we got from the previous one, right? So we're going to XNOR that. XNOR the truth table or lookup table is 1001. And so that implements this 3-input XNOR, like that. So hopefully that makes sense. Yeah.
I think so.
No problem. Are they used for decoders and selectors as well? Similar, right? Off topic, a friend of mine is asking for a cast name. Her name is Rosie. 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 And now she wants to sit on my lap again, I think. So she can come here. Okay, so she might make a cameo again. We will see. Anyway, so that's 3B. So let's move on to, we can do question 4, or we'll do question 4 as like a decoder. So maybe we can talk about that a little bit, right? This decoder. And it says, yeah, okay, we can do this. I think it's helpful to learn a little bit about how decoders work. And then question 5 is like a Shannon expansion. Let's do the Shannon one actually now, because it related to multiplexers, right? So it says use only 2-to-1 multiplexers to implement the following function. So a 2-to-1 multiplexer is like a 4-to-1 multiplexer, but smaller. So it has only 2 inputs, 1 control bit, and 1 output, right? So if this is A and B, right? So if C is 0, then this will be connected. If C is 1, then this is connected. Right? So that's everything. I think she wants to leave. So no more cat. So now so it says, implement the following function. Shannon expansion is a particular way that makes it very helpful to implement these functions using multiplexers. So we can do that. So let's do it here, right? Let me see. So the function that we are implementing is this, right? So we can do like a little K-map first, right? So it's the K-map. So we did this in lab 2, right? So we have our, it's been a minute since I've done a K-map. So we're going to have our X1, we can do it like this, right? So we can have our, X1, X2 here, and X3 here, sure. Actually, I usually do it the other way, right? But how do we do in the lab? We did it with 4. So we had I had it like A, B, C, D. It doesn't really matter. So let's just do it however. So we can do our, we'll do it like this because this is how I usually remember to do it. So it's X1, no, I'll do it like this. I'll do X1, X2, and X3, like that. Right? So then the values here are going to go, no, that should be X1. It makes more sense to write like that, doesn't it? There we go. That's good. So this is going to be 0, 0, 0, 1, 1, 1, 1, 0, like that, right? And then we have 0 and 1. So remember the flip there. In my lab section, I asked you what the flip was for, right? And so we can maybe talk about that here. And then, so then we implement all of this, right? So we have like 0, 0. So 0 is going to be here. So that's going to be a 1, right? And then 3 is going to be, be 0. 3 is what? 3 is, depends on the order you're doing it in, I guess, as well, right? So maybe we can make a truth table first, right? So we have X1, X2, X3. And we have our function, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1. And so then we have 0, 3, 0, 3, 5, and 7. No, that's not 5. That's 5. And then that's 7, like that, right? And then the rest of them are zeros. So we have this kind of looking like that. Okay, and then so now we can kind of map it all together. So 0, 0, 0, 0 is there, and then our next one is going to be at 0, 1, 1. So 0, 1, 1, like this. And then the next one's going to be at 1, 0, 1. So 1, 0, 1 is going to be right there. And the next one's going to be at 1, 1, 1. So 1, 1, 1 is right there. So there's our kind of K-map kind of thing, right? And then now we want to make, we do the K-map for it. So the K-map for it will be, well, you have, this is alone. There's nothing to match that with, right? These form a group of 2 and these form a group of 2. And I'll just mention that this is also something that just is good for K-maps. Like you don't group this just as 1, you group it as 2. You group it as 2. We want to make as few groups of 1 as possible. So hopefully that makes sense. Now we need to actually make our expression for F based on this, right? So for this group 1, they're all zeros, right? So it's X, not X1, the not x2 and not x3. Or, and then let's do the second group here, which is these two, right? So we just look at what is staying the same between the two, right? So we have what's staying the same. So we have like in between these two groups, right? This is going to be 0, 1, 1. 1, 1. Someone said something. Wait, sorry, isn't 1, 1, 0 equal to 0? Yeah, 1, 1, 0 is equal to 0. And 1, 1, 0 is equal to 0. It's kind of read like the order is given here, right? Yeah, exactly. Right? So then, so here, right, we have x2, x3 for this one, right? Because x3 is staying the same, obviously, positive, x3. And x2 is staying the same, positive. So it's x2, x3. And then the third group, again, we're just doing what stays the same. So it's again going to be an x3, but this time it's x1. So it's x1, x3 staying the same. So just what's staying the same between the bits. Hopefully that makes sense. So this right here represents 1, 1, 1. This represents 1, 0, 1. So you see the first and the last bits are the same. So for group 3, x1 and x3 are the same. So they're part of the term there. Okay, so well, someone's asking if you can group the corners. So remember, the grouping the corners, you can make groups if there's only one thing changing between them, right? So this bit right here is going to be 1, 0, 1, and this one right here is 0, 0, 0. But two bits are changing there, so they cannot be grouped. It's only like when it's a 2 by 2 or 4 by 4. So they cannot be grouped. Hopefully that makes sense. Yeah, so let's see now. We need to do a Shannon expansion. So the point, and it says use x2 in the case of Shannon expansion. So the point of the Shannon expansion is that we can take all this, right? Call that F0 maybe, or something like this, right? Or it's F, I guess. And we can rewrite it as x. So it says use x2, right? So we can have not x2, f, and then I'm going to say f of x2 equals 0, or x2 and f of x2 equals 1. So it's just kind of a way to separate it out into two cases, right? Where we have x2 is 0, so then you can write the expression of what x2 is 0 and it with not x2. So if that's true, then x2 is 0. And then otherwise we have x2 is 1, so we can break that into the other case there like that. So so now we just write that expression. So I'm going to turn my fan a little bit to the side. Okay, so now let's do it. Okay, so here we have x, not x2, and we need to evaluate this expression when x2 is 0, right? So when x2 is 0, this term is 1, so then we just have x1, should be x3 there, right? x2 is 0, so this term goes away, and then we just have x1, x3 like that. So hopefully that makes sense. And then x2, we evaluate the expression when x2 is 1. So if x2 is 1, this term goes away. We just have x3 or x1, x3 like this. So the point of this is that it's kind of like now I have a multiplexer where my control bit is x2. If it's a 1, into here I want x3, x1, x3. And if it's a 0, I want x1, not x1, not x3, x1, x3. You see how like that's not the final answer, but I've done something kind of here, right? I've rewritten it in a multiplexery kind of way. It's 0, 1, right? So if x2 this seems right to me. Oh no, yeah, sorry, this is flipped. My bad. Yeah, I don't know why I did that. So that's right. Thank you for noting that. Yeah, that's correct. So this is, we've rewritten it in like a multiplexery kind of way. So we can just try to keep simplifying it because these expressions right here are not right now able to be written as two input multiplexers just yet, but you know, give it a second, right? So we can simplify this a little bit, right? So this expression right here, which maybe we'll call F1. So F1 is X3, different color. I don't really like writing in that color. So call it this F1. So F1 is X3, X1, X3. But of course, you can just take out the X3. You have 1 or X1. And 1 or X1 is 1. So this is just X3. So that actually, that whole thing is just X3. That's helpful. So we can just wire that in. Great. And now to the top, we need to somehow involve X3 and X1 into this expression. And again, you can just do another Shannon on this, right? So you can call this F0, right? So then F0 is not X1, not X3, or X1, X3. And then again, we can just pick some variable, I don't know, X3, whatever, right? Let's just pick X3. So we can write it as X3 and whatever happens when let's say, and F0 where X3 equals 1, or not X3, I guess maybe, maybe I did it the other way, so let's do it like this. So, or X3 where F0 with X3 equal to 1. So hopefully that makes sense. Yeah, right. So someone's just asking about this step right here, right? So 1 or X1. Well, let's just go through it. If X1 is 0, then it's 1 or 0 is 1. If X1 is 1, then it's 1 or 1, it's 1. It doesn't depend on X1 at all. Like this expression right here does not depend on X1 at all. It's just X3 and 1. Right? So maybe I'll write that. This is 1 plus X1. Right? And then X3 and 1 is just X3. For the similar reason, right? It just depends on X3. So hopefully that makes sense. Yeah. If you're ORing something with 1, it's just going to become 1. Doesn't matter what the other thing is. So then we do this expression. So we have not X3. With X3 being 0, it's just going to be X1, right? Not X1, like that. And then with X3 being 1, it's just going to be X1. Right? And so there we go. There we have that. And so now our circuit is kind of expanding here, right? So we had this. This is kind of what we did. But now this expression here, as we said, is just going to be X3. And this expression here is going to be the result of another multiplexer, this time with the control signal X3. And the input for when X3 is 0, we want not X1. And when X3 is 1, we just want X1. And the final thing is, again, I can't use an inverter. Like I'm not allowed to use an inverter. It says only 2-to-1 multiplexers. So we just need one more multiplexer here, right? And that's just going to be inverting based off of the signal from X2, right? X1, right? It's not X1 that we want here, right? So if it's just going to invert the signal like that, right? So if it's like hardwired here, 1, 0. So if X1 is 1, this will be 0. If X1 is 0, this will be 1. And then it flips it, and then we have that like that. So that's our full circuit. That's been expressed using Shannon a couple times, twice, technically 3 times if you want to do it for the inverter. And we keep expanding it into being implemented as multiplexers. So that's kind of the full answer there. Someone's asking about if we will be getting the Boolean algebra formulas. I have no idea, unfortunately. That is a question for the prof. Let's see what the announcement said. Announcement doesn't say anything. Someone said, I'm pretty sure he said we wouldn't. So it's a no. Yes, PDF will be posted. It says that here. But yes, PDF will be posted. Okay, guys, well, it is approximately time to wrap it up, unfortunately, but I think we got through some really good questions here. I mean, these are circuit design questions I think are helpful, and I would expect to get a Shannon kind of question, a CMOS kind of question, a numerical kind of question, and a lookup. Like, these are all things I would expect to see on the midterm for this kind of course. So it's good that we got through it. Yeah, it is approximately time to wrap it up, though. So I'll spend just it's the last question I'll do, but I'll stick around for a few more minutes if people have questions they would like for me to answer, just general ones about the recording. I will post it right now, and then it'll be on
Recording
my YouTube channel
stopped.
in an hour, let's say, or something like that, when it finishes processing. And yeah, notes will be posted in about an hour. And yeah, okay. So otherwise, I mean, that's the last question. So if nobody has any questions, then I'll wrap it up there. But again, I will stick around for a minute. Yeah.
Can you go down to the last part that you did for the?
Yeah. Can I ask how to draw the logic gate connections for a full adder? Recording will be on my YouTube channel. Yes. Draw the logic gate. What do you mean exactly by logic gate connect? Oh, I guess you mean like so if I have a full adder, right? And I have like carry in X, Y, and I want to have I want to have sum and carry out, and you want to see like the logic gates inside is what you're asking, right? So that's fine. So then this is the same thing as if we have like two half adders, right? So we have a half adder that adds C in and X, and this will have like a sum and a carry out. And then so we added those bits together. And then we have another half adder, right? And this half adder has to add, what does it have to add? It has to add the Y and the carry out from here. Like it has to connect these two. Like that. So I'll just put that there, right? And this has a Y there. And then this will be our first bit of our, this will be our sum coming out. And then this will be our C out, like that. So hopefully that makes sense so far. That's another half adder. And then, so that's in terms of half adders. And then the half adders themselves are relatively easy to draw. So we have like a C in and we have like we have two sums, right? We have an X and a Y. Let's call it an A and a B or something like this, right? Then you have an S and a C out. And so the point is, so these are equivalent. The point is that, okay, so we have our A and a B, we have an S and a C out, and then what is it? We said the half adder up here, right? You can see for the half adder, the S is XOR and the C out is AND, right? So the S is an XOR of the two signals, and the C out is an AND of the two signals. However you want to draw that. So that's how you draw a half adder, and that's how you draw a full adder in terms of half adders. So hopefully that makes sense. For the 2-to-1 mux, for the second part, could you have done like factor x1 instead of x2? Yes, you could have, for sure. There's multiple ways of doing a Shannon decomposition. There's multiple, You can have different layers. Some are simpler than others. It didn't say optimal here. It just says use Shannon expansion. Well, I mean, it didn't really say that, but that's what it's implying, certainly, and you have to do it like that. All right, that's all the questions for now. So I'll stop recording on my end.